Talk about the Bronsted-Lowry definitions of acids and bases. Let's start with the acids. You may recall from general chemistry that an acidic substance is one that donates an H plus from the point of view of Bronsted and Lowry. In doing so, you create your conjugate pairs. You have conjugate acid, conjugate base, conjugate acid. And as long as your molecule has H's, it can behave as a potential Bronsted-Lowry acid. Needless to say, organic molecules, the vast majority of them, contain at least one hydrogen within the molecule. And so each one of these molecules could potentially behave as an acidic substance. Now, to what an extent this will happen will depend ultimately on some chemical characteristics of the different functional groups, and we'll talk about that in a little bit. But first, let's talk about what a base is from the point of view of Bronsted and Lowry. Simply stated, acids do the opposite than bases, and what that means here is that a base will not be donating an H+, it will instead be accepting an H+. So in this case, we have water donating an H+ to the base A-, creating HA and hydroxide. That's your typical equation, your balance equation for the base dissociation of A-. So technically speaking, as long as you have lone pairs present in your base, this can happen. All right, now one thing we're going to use plenty whenever acid-base chemistry is invoked in organic mechanisms is conjugate acids and bases. We need to be able to draw these things directly from the corresponding reactants, and so that we'll use this information to kind of build a repertoire of mechanistic explanations. So looking back at this acid dissociation of HA, the substances are going to differ only by one H, right? So HA and A-, they only differ by one H. H2O and H3O plus differ only by one H. And if we are technical about it, this is an H plus. Difference is based on a unit of charge and a single amount of hydrogen. So water and H3O plus represent a conjugate pair. HA and A- represent a different conjugate pair. Within the conjugate pair, the one that has the most H's is the acid. Whichever has the least amount of H's within the pair is the base. Same thing here, between water and H3O plus, water is the base because it has the least amount of H's, and hydronium is the acid because it has the greatest amount of H's. Another feature that you see arising here automatically is that regardless of whether you're on the reactant side or the product side, acid mixes with base. Base mixes with acid. You will never have acid plus acid or base plus base. So it's something to keep in mind. Same idea for the base dissociation of A-. Between A- and HA, we have a conjugate pair. Between water and hydroxide, we have another conjugate pair because the difference is only of a single H and a single charge. Between A- and HA, the one that has the most H's is a species considered to be acidic. So this is the acid, and the base is A-. Between water and hydroxide, water has more H's, so that's the acid, hydroxide is the base. And once again, reactant side we have base plus acid, product side we have acid plus base. We will never have acid plus acid, we will never have base plus base. So keep that in mind. Alright, now in terms of looking at the organic molecules, because all these molecules have H's and they can behave potentially as acidic substances, you could generate the conjugate base of each one of these substances. And to do so, what that would mean is that you will have to remove an H+. Remember that the hydrogen present in the molecule is part of a carbon-hydrogen bond, or an oxygen-hydrogen bond, or potentially a nitrogen-hydrogen bond. when you remove an H+, the electrons are left behind in the molecule. So notice what happens, for instance, to this alkane when you draw the conjugate pair. The conjugate pair now has a lone pair on the carbon, and that's because the H+ is now gone. The H+ that used to be part of this bond is gone, and now you have a lone pair. In addition to that, because the H+ has been lost, the charge has dropped by 1 unit. The alkane was neutral, now it bears a -1 charge. And notice that we're doing the same thing here with the alkyne. That CH is removed, you end up with a carbon with a lone pair and a negative charge. Carbon, lone pair, negative charge. Pretty much that's true every single case of the way. And for the carbon atoms that bear the negative charge, we call them carboanions. And that's very characteristic of organic molecules. We're going to kind of focus entirely on that carbon and come up with some terminology in association with carbon. So it's not just an anion, this is a carboanion. And then for your carboxylic acids or your alcohols, you do remove the H from the oxygen. That tends to be the more acidic position. And when you do that, the alcohol becomes what we call an alkoxide, and the carboxylic acid becomes a carboxylate. And this is kind of reminiscent of what happens with like nitric acid. Remove the proton, it becomes nitrate. Sulfuric acid becomes sulfate. Carbonic acid becomes carbonate. So carboxylic acid becomes carboxylate. And this is something I want you to be very good at in terms of naming molecules, right? So carboxylate is the conjugate base of a carboxylic acid, and alkoxide is the conjugate base of an alcohol. The other ones we're just going to keep them name-wise the same. Okay, so aromatic, you have your carbanion. Your amide, you remove a proton from the nitrogen. You have your not your carbanion, but you have your conjugate base. And as you saw, all it took was just remove that extra proton, decrease the charge by 1 unit. That's all it took to draw the conjugate base. All right. In the next video, we're going to talk about the definition of pH, pKa, and we'll look a little bit about how to predict reactions just by looking at the pKa value. So see you then.